This narrated slideshow is about the things people do to save their beaches. As you'll discover, the beach is rarely the problem. Beaches, by their very nature, move around. They migrate, they grow, they thin, and it's only when people put structures on or near them that the problem of beach erosion arises. Here, for example, is a natural beach. It's healthy, even though the beach has migrated so fast that trees that were originally located behind the dunes are now located right on the recreational beach. Now, they're going to die eventually because they're sitting in an area that is inundated with salt water and because the waves will knock them over. But notice that the sand, however, is fine. The beach is fine. It hasn't disappeared at all. Here's another beach. A storm has taken a good-sized bite out of the dunes, but that's what it's supposed to do, right? That's the way a healthy beach responds to storm events. And this wouldn't be a problem at all, except that people put structures on the dunes and now these structures are destroyed. So in this case, the beach is now deemed to be an eroding beach, even though the sand is still there and the beach is still fine. In order to fight perceived beach erosion, engineers adopt three different strategies. First, they can try to keep the sand on the beach from moving. Second, they may try to trap the sand behind walls and keep the waves from affecting the structures on the beach. And third, they simply import more sand to replace the sand that's been removed or sand that's been moved. A groin is a rigid structure built perpendicular to the beach for the purpose of trapping sand moving via longshore drift. In most cases like this one, groins appear in sets of equally spaced barriers. The groin works by trapping sand on its updrift side, which in this photo is to the right. Unfortunately, there's no free lunch. The accumulation of sand on the updrift side is balanced by an erosion of sand on the downdrift side, to the left. The downdrift erosion often causes a downdrift neighbor to erect another groin, and so on it goes. Pretty soon you have this situation, a long row of groins, each one capturing sand on its updrift side and suffering erosion on its downdrift side. And the net effect on the beach is zero, the sand simply being redistributed. A jetty is a similar structure. It's also perpendicular to the shore, but it serves a very different purpose. A jetty is designed to interrupt longshore drift and keep it out of an inlet, keeping the inlet clear for usually navigation. Here we can see an inlet with jetties protecting it on both sides. Longshore drift is being deflected away from the shore. Jetties are usually longer, higher, and more intrusive than groins. They may have a profound effect on the shape of the coastline. Notice the offset in the coastline here. The sand has accumulated behind the jetty to the right and been eroded away from the jetty on the left, which has caused the land to the left to actually migrate shoreward. This is the typical response of an inlet to jettying. One of the most famous examples of this occurred at Ocean City Inlet in Maryland. Longshore drift in this area is from north to south. A jetty built on the northern side of the inlet caused so much erosion on the downdrift side to the south that the inlet here migrated nearly 1 kilometer in 50 years. Here's another example at Matagorda Channel in Texas. Can you tell which way longshore drift is moving here? If you said this way, you're right. A breakwater is a different strategy for retaining sand. A breakwater is built parallel to the shore, not perpendicular like a groin or a jetty. Its purpose is to produce an area behind it where there's calm water where sediment can accumulate. As the energy of the water decreases behind a breakwater, sand is deposited. So much sand may accumulate that the breakwater soon becomes joined to the land, producing what geologists call a tombolo. When this happens, the breakwater becomes the de facto beach. The picture on the bottom shows what it looks like when this happens. Although there's sand behind the breakwater itself has become a hazard as waves break directly on the rocks and strong currents make it difficult to avoid. The last resort of shoreline engineers is the seawall. A seawall is nothing more than a rigid wall built to protect structures. I emphasize structures because the presence of a seawall accelerates the loss of sand in front of it. So while the structures may be saved, temporarily at least, the beach in front of it is inevitably lost. This loss occurs because wave energy can't be dissipated against sand like it usually is, but is concentrated at the base of the seafloor. The reflected wave energy stirs up sediment and carries it away. There is often a depression or trough where waves have scoured away sand at the base of the seawall. The wet sand in this photo is the trough at the base of the seawall. Where a seawall ends, there are often edge effects where focused wave energy leads to enhanced erosion. The edge effect allowed waves to attack this swimming pool from the back and side, even though it was protected from frontal assault by the seawall. In an attempt to soften the effect of a seawall and allow some of the wave energy to be dissipated, geologists sometimes use piles of rock instead of smooth surfaces. These piles of rock are called riprap. Sometimes the riprap replaces seawalls, and sometimes riprap is placed in front of seawalls. Here, engineers have placed riprap in front of a seawall. Their efforts, however, have been in vain. The sand is already gone, and the property owners here can look out over the dangerous rocky shore from the safety of their balconies. Probably not what they envisioned when they bought this beachfront property. So it's a trade-off: preserve the property or preserve the beach. Here they've chosen to preserve the property. Eventually, even the stoutest seawall will fall victim to the waves of a large storm. And when this happens, the beach is further marred by the broken up pieces of the wall. In some cases, like in Florida, the government has decided against any kind of structure and in favor of a simpler solution, or rather a less invasive, intrusive solution. Simply import more sand whenever it is needed. It's needed a lot. In some cases, this renourishment of the beach has to take place every couple of years. Here's a renourishment project underway in Pinellas County. In most places, the source of the new sand is offshore. It's pumped onshore as a slurry and then bulldozed around into position to create something resembling a beach. Mother Nature then takes over and shapes it the way she wants. Here's a great time-lapse movie showing what a nourishing project looks like. Sand is pumped onto the beach from ashore as a slurry through pipes, and then the bulldozers push it around and they shape the beach and distribute the sand evenly, and then they move farther down the beach to repeat the whole process. And then eventually, when they're done, Mother Nature takes over and does her job. The effect can be dramatic. Compare these before and after photos of Sand Key in Florida. The extra layer of sand protects the structures along the coast from storms. One issue for nourishment is finding the right sand. If the sand is too fine-grained, much of it will be picked up and trained and washed away by the waves. Some fines are inevitably lost following nourishing. Here you can see it clearly in this photo where that cloudy water represents fine material that's been picked up and will be lost from the beach. A map of nourished Florida beaches basically shows Florida beaches. Nearly all of the famous white sand beaches in Florida contain sand that's been brought in from some other place.